Hello, my name is Sriram Rajagopal, and I'm presenting from California, USA, about TalusNet, a fully convolutional neural network for talus slope detection using terrain and imagery. So what are talus slopes? Talus slopes are naturally occurring slopes made of a jumble of loose rocks that have fallen from a rocky cliff or other rock face above. And below, you can see an example of what a talus slope looks like. So why did I research this topic? So rockfall is a pretty dangerous phenomenon. On the 8th of January 2022, rockfall occurred in Brazil, killing 10 people and leaving 32 others injured. Talus slopes are a precursor to rockfall and landslides, and so finding talus slopes can help people take preventative measures against things like these. Data collection. So I decided to gather data near the Kings Canyon National Park, since I already had access to a map of existing talus slopes in that area. To train the model, I needed input data. More specifically, I needed elevation, satellite, aspect, and slope data for the Kings Canyon research in order to begin training my model. To get this data, I used the USGS National Map Downloader. A convolutional neural network, more specifically UNet, was used to analyze the data and find talus slopes. And you can see an example of the UNet architecture to the right. But what is a convolutional neural network? Well, a convolutional neural network is a type of neural network that works exceptionally well with images, speech, or audio. This approach fed the model data in order to create a black and white image using a technique called binary semantic segmentation. What is binary semantic segmentation? Well, it's a process that creates an image where a black pixel means the model predicts a talus slope doesn't exist at that location, and a white pixel means the model predicts a talus slope does exist at that location. So overlaying this image over the area of interest would let the user know where the talus slopes are. And there's an example below with the human. So on the left, there's a picture of a normal human. In the middle, there's the binary semantic segmentation map, where the black pixels are where the model predicts the human doesn't exist, and the white pixels where the model predicts the human does exist. And then on the right, there's the overlay showing how accurate the model is. The data collected from the USGS National Map Downloader was imported to Google Earth Engine, where it was correctly formatted and ready for use in the model. And below you can see a snippet of code from Google Earth Engine. Creating the model. Now that the data collection was over, it was time for me to begin work on the model. The first part of the model would be to process the data a bit further. I combined the data together to create chunks containing information about the slope, aspect, color, and elevation of the selected area. Next, I created the UNet portion of the model based on the outline shown below. Once the model was created, I could begin training it using the data chunks. So after running the model through many iterations, I finally found one version of the model that worked exceptionally well. And the results are shown below. As you can see, the predicted binary semantic segmentation map is extremely close to the actual one. And we have metrics to back this up as well. So there are four main metrics: accuracy, precision, recall, and F1 score. The closer these values are to 1, the better. And since all of these values are very close to 1, this model was very good. To the right is a confusion matrix, which displays how accurate our binary predictions were to the actual values. And we were very accurate, only getting about 3% of the predictions wrong. So how would I take this further? Well, in the future, I'd love to experiment using the same data and a similar algorithm to identify other geological features in hopes of creating more beneficial mapping technology. Thank you.